Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're going to do a theory video, super quick, on entropy. I want you to have a better mental model of entropy so that you can solve the problems, the thermodynamic problems, in a way that's hopefully more intuitive. So let's talk about entropy. A lot of students, when they learn about entropy, they learn about this idea of disorder, and that's fine in the beginning. But really, entropy, it's better to be understood with the idea of multiplicity. And multiplicity is a fancy way of saying the amount of different ways a system can be arranged, the amount of different ways a system can be displaced in time and space. Okay, so what we have here is a control volume. I just have a box for now, and we're going to make this super simple. Okay, so we're going to talk about three different things. We're going to talk about temperature, we're going to talk about pressure, and we're going to talk about state of the matters. Pressure and state. Okay, we're going to talk about each of these separately, and like I said, it's supposed to be a quick video and supposed to be a video to assist in your mental modeling of entropy. Okay, so let's, in our control volume, let's put a single molecule, or a single atom, if you will, right there. Okay, so we just have that one atom, and it's bouncing around, it's floating in this one box that we have here. So it can be here, it can be here, it can bounce here and come back, it can go around, etc., etc., etc. Each of the spaces inside this box that I have can be understood as an arrangement, a possibility of places in which this atom or this molecule can be, right? This is a simplification because obviously, we can also have rotations, we can have, this is 3D, so there's different specifics within these states, but let's just think about the position of them as being, as being a possibility of where it's going to be. Let's just increase that so we can grab it easier. Okay, now, what is the deal with temperature? Let's talk about temperature first. So temperature, we know, is a indirect way of measuring the activity of our molecules, right? So the greater the temperature, the more kinetic energy these molecules and atoms have, so they can move around. So if you think about, something with higher temperature is going to have this guy bouncing around up and down more and more and more, right? Now, if I have, let's take it to the other extreme. Let's take it down to 0 Kelvin, right? So absolute zero, so that, this molecule is literally frozen. It cannot move whatsoever. If it cannot move whatsoever, the only position it can be, right, in all possible dimensions you can think of, is the way it is right now, right? So that is the lowest possible entropy the system can have, right? So there's only one possibility. So there's, going back to the idea of multiplicity, there's only one possible place arrangement for this guy, which is the way it is right now, right? And if it could be any other way, it could be here, it doesn't matter. Let's say it was here, and then 0 Kelvin, all right? So this is the lowest order of entropy I can possibly have. What happens as I start to increase my temperature? Well, as soon as I increase my temperature above 0 Kelvin, this guy starts to move. So now it can be here, it can be here, it can be here, it can be here, it can be anywhere, right? So as I'm increasing my temperature, I'm increasing the probability of increasing the number, I should say, number of states in which this guy can be. Okay, so this is the first way that we're going to think about entropy today. We know that the higher the temperature, the higher the entropy for a given system, isolated system like the one we're talking about here right now. Okay, closed system. All right, so now what happens if I introduce a second molecule? Right there. Okay, now I have two of them, right? Remember that pressure, now we're moving on to pressure. Let's get rid of this guy and just highlight we're moving on to pressure. Remember that pressure is a measurement of how, I should probably leave that, right? Remember that pressure is a measurement of how these guys are bouncing and exerting force, right? Pressure is just force over area, exerting force into the boundaries of my system and against each other, right? So as soon as I introduce a second molecule, what I'm doing is I'm increasing the pressure, because now I have two molecules that are going to be hitting the walls back and forth, and I have molecules that can hit each other. Whilst before, when we didn't have this second molecule, this guy could only hit the boundaries, right? So we just increased our pressure as soon as we introduced that second molecule there. What else have we introduced when we do that second molecule? Well, we have increased the number of multiplicity, right? The multiplicity, I should say. The number of different positions these guys can be in. So now think about this. Remember when this guy was frozen, right? And let's say it's frozen where it is right now. Well, there was only that one state. What if this guy was frozen, but this one was not, right? It's a, far-fetched state, but, what about that? Well, I still have multiple different ways this can be arranged, right? Even though that guy is only the same, always in the same position, this guy can be in several different positions, meaning that my multiplicity is higher, right? I have more states in which this guy can be in, right? So as I'm increasing my pressure, and we can do that for, right, we can introduce as many molecules as we wish here. As I'm increasing my pressure, I'm also increasing my the number of states I can have in. So I'm also increasing my entropy, right? So as my pressure increases, my entropy should increase, again, for this closed system here, specifically that we're talking, okay? And lastly, now let's say we have all these molecules, and it's steam for that matter, we can do that. And let's say that I'm going to now, condense this, and I'm going to then solidify this so that I'm going to combine all these molecules into one block of ice. Okay, so this is now a block of ice, and all those molecules that were free before, they are now arranged in this structure here. What have I done? I have decreased the number of possibilities. Well, these atoms now, they will only be, confined within this cube of ice, which, note, is smaller than my original arrangement, right? So now, if you think about this, as I went from, a gas or a liquid into a solid, I've decreased my entropy, right? I've decreased the number of states this guy can be in. So when we talk about states, state of the matter, right? So solid, liquid, gas, we expect the solid to have a lower entropy in respect to the fluids, right? And now we can reverse this. Obviously, I can start to heat this up, and I can start to allow these guys to go loose. And as soon as this becomes a gas or fluid, guess what? Now these guys are going to, oops, you probably can do that. Now these guys are going to move around, right? So now these guys can go here, and these guys can go here, and you will occupy all the volume of this container, right? Of this box that we're simplifying, right? And obviously these here, and etc., etc. So what happened now? I've just increased the multiplicity of the system. I just increased the number of states, possibility of states in where these molecules can occupy. So guess what I'm doing? I am increasing the entropy, right? So we can, again, as a simplification, and for a good mental model, right? And when you're solving the problem, this is going to be useful. For a good mental model, we can think about solids as having a lower, and let's put it this way, let's do it this way, make it more palatable. Entropy of solids are lower than the entropy of gas. Okay, so again, very simple, straightforward, just these three ideas of how the entropy should change with temperature, pressure, and the state. And we can actually verify this. If we go into, property tables, we can check at, entropy here, and we can see, for instance, this is a saturated liquid. So we're going from liquid to vapor. What's happening with the entropy? It's increasing, right? I have more states in which the molecules can arrange themselves in a vapor than I have in a liquid, right? Precisely because of what we just talked about.